In this unit, we'll focus primarily on the behavior of solutions, and specifically how acid-base chemistry has influenced how water forms specific types of ions in solution. A solution is simply just a homogeneous mixture. And when we talk about aqueous solutions, we talk about the solvent and the solute. The solute is the substance that is actually being dissolved, and the solvent is the substance that is doing the dissolving. Another way to keep those two terms straight is that the solute is usually present in a much less quantity, and the solvent is usually present in a much higher quantity. When those two things are mixed, the homogeneous mixture without any layers is referred to as a solution. During the formation of a solution on a microscopic level, that we see right on a macroscopic level that salt appears to dissolve when it touches water, but really what's happening is the salt is starting as a crystal lattice of alternating positive and negative charges. Water happens to be extremely polar, and the positive side, or the hydrogen side of water, is very attracted to the negative ions. The more electronegative oxygen is more negative itself. It's attracted towards the positive ions, and water does a very good job of separating those ions that were once stuck together in that crystal lattice. The reason why water is able to do this is because of a very special intermolecular force called an ion dipole force. Ion dipole forces begin to form when water molecules are able to surround cations and anions in solution. In the case of a negatively charged ion, that negatively charged ion opposites attract, and the slightly positive hydrogens are attracted towards that negative anion. And you can see that the water molecules begin to form a cluster around that negatively charged ion, and that helps it to stay separated from the other ions in solution. Positively charged ions are more attracted towards the negative oxygens, but you can see the same sort of cluster will form around a positively charged cation. As a quick concept check in terms of the strength of intermolecular forces, why do you think you can explain in words why ionic compounds dissolve so well in water? Take a moment to see if you can answer that yourself, and we'll go over the answer here after you pause the video and try to write a written response. The reason why most ionic compounds do dissolve very readily in water is because ion dipole forces are typically much stronger than the combined forces of the water molecules having hydrogen bonds attracting other water molecules to those H2O molecules, and the chemical bonds that exist within the crystal lattice of the ionic compound itself. Those two forces are relatively strong, but the ion dipole forces that are able to form between water and the positive and negative ions is much stronger than those two forces, and that's why most ionic compounds will dissolve very quickly in water. Solubility is defined as the ability of a certain solute to dissolve in a given amount of the solvent. One of the ways that this can be expressed is the grams of solute that are able to dissolve in 100 grams of water. This chart is referred to as a solubility chart, and you can see that for most ionic compounds, they become more soluble, or they have a higher solubility at higher temperatures. So you can see here at 80 degrees Celsius, this compound has an approximate solubility of about 120 grams per 100 grams of water. Along this line, we say that the compound that we're looking at is saturated, which means that really no more of that solute should dissolve. Any amount of that solute that is below that line is considered to be unsaturated, which means that if a compound is approximately here on the graph, we can still add more of the solute until we get to that maximum saturated level. Now, can we exceed that? Certainly. Sometimes we're able to heat up a solution to a very high temperature, let it cool, and some of the ions will stay suspended in the solvent more than should be dissolved at that temperature. If a solution has more of the solute dissolved than what the saturated line would predict, we say that that solution is supersaturated. Supersaturated solutions are extremely unstable and will spontaneously crystallize if they're disturbed or if they're shook or if dust gets into them. So supersaturated solutions can be created, but usually they're very unstable. There's a few different ways that we can increase the solubility of an ionic solid. Most ionic solutes dissolve more effectively at higher temperatures. We said, according to kinetic molecular theory, at higher temperatures, particles are moving with a higher average speed. So the speed with which water molecules are able to surround ions is increased at higher temperatures. You can see that most ionic compounds will become more soluble at higher temperatures. Some don't, but for most ionic compounds, they do get more soluble at higher temperatures. A second way that we can increase the solubility of a solute is to simply just break it into smaller pieces. This vastly increases the surface area. If you have more surface area for each of those particles that you're trying to surround with water molecules, you're going to open up more opportunities for those water molecules to form intermolecular forces with the solute. So more surface area is going to help the particles attract more effectively to the solvent. An example of this is when you crush up Alka-Seltzer tablets, they'll bubble and dissolve much more quickly. When you're mixing two things, usually a solvent with a similar polarity or similar types of intermolecular forces able to form will help the solution process to occur. So when a solid is held together by certain types of intermolecular forces, the solvent is able to attract to that solute if they contain similar types of intermolecular forces. The general rule is, right, like dissolves like. So if you want to dissolve something that is polar, you would better use a polar solvent. If you want to dissolve something that is nonpolar, it's better to use a nonpolar solvent. Our next lesson is going to move into how we quantitatively measure the concentration of solutions with numbers. And that will be our next mini lecture.